Good afternoon, class. Here's exam 3 review covering chapters 3 differentiation rules and application of differentiations from section 3.9 to 4.5. And here's section 3.9 related rates. We're going to cover 3.9 related rates, linear approximations, hyperbolic functions. Then we move on to chapter 4, application of differentiations, 4.1, maximum and minimum values, the mean value theorem, how derivatives affect the shape of a graph, indeterminate forms, and L'Hopital's rule, summary of curve sketching. As always, there is a pledge. When we take the exam, we take the exam on our own. Differentiation formulas, starting with definition. dy dx is limit of delta y over delta x as delta x approaches 0. And the limit of f of x plus h minus f of x as h approaches 0. Then we look at the power rule, trigonometric functions, product and quotient rules, chain rule, exponentials, logs, limit for sine, and the inverse trigonometric functions. Now, related rates. If we are pumping air into a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume than the rate of increase of the radius. So, in a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. Procedure. Number 1, find an equation that relates the two quantities. Number 2, use the chain rule to differentiate both sides with respect to time, meaning t is the only independent variable. And that's really the key. Therefore, dy dt is dy du dt in that format. As a warm-up example, air is being pumped into a spherical balloon so that its volume increases at the rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So what is given? What is missing? Given is the rate of increase of the volume of air, which is 100 cubic centimeters per second. Missing is the rate of increase of the radius when the diameter is 50 centimeters. So what do we need to know? First of all, here's a spherical shape with the volume being 4/3 power cubed, and d, of course, is 2 times the radius. And having said that, let's put this in symbolic format. First of all, we should know this volume is 4/3 power cubed for the sphere. Now, this one is dv dt is 100 cubic centimeters per second. What are we looking for? dr dt, when d is 50, and r, which is half of that, 25 centimeters. So this is the translation of the question into mathematical symbols. So simply put, we want to differentiate this with respect to t, dv dt. And so the intermediate variable from v to t is also dv dr dt according to the Leibniz's notation. So I want to take a derivative of this with respect to r first. Obviously, 4/3 pi is a number, is a coefficient, and it remains unchanged. So you write that. Then you differentiate r cubed, gives you 3r squared. And because r is a function of time, it's times dr dt. So it's 4 pi r squared dr dt. If I want to find dr dt, I'm going to divide both sides by 4 pi r squared. And now I can plug in. dv dt is replaced with 100. 4 pi r is replaced with 25. So over 4 pi times 25 squared. As you know, 4 times 25 is 100. So we're going to say 4 times one of those 25s, cancel out the 100, we get 1 over 25 pi. This is the precise answer, which is positive, and that means increasing. So the radius of the balloon is increasing at the rate of 1 over 25 pi precisely, or roughly 0.0127 centimeters per second. Please understand you answer accordingly and however they want it with however many decimals. A small rock is dropped into a lake. Circular ripples spread over the surface with the radius of each circle increasing at the rate of 3/2 feet per second. Find the rate at which the area of a circle is changing when the radius is 4 feet. But first and foremost, we are dealing with a circular shape, which means we should know the following. Starting from the center, go to the circle is the radius, go to both sides is the diameters, d equals to r, circumference going around it is 2 pi r, area is pi r squared. We know all of them and we need the area equals pi r squared. Let's go back and continue reading. With the radius of each circle increasing at this rate, that means dr dt is 3/2 feet per second. What are we looking for? Rate at which the area is changing. That means dA dt at a precise moment where the radius is r equals 4 feet. So this is translation of the question into mathematical symbols. So having said that, we have A equals pi r squared, and we need to find dA dt, which means pi, it's just a number. So you keep it now. Differentiation of r squared is 2r dr dt, because t is the independent variable, or simply put 2 pi r dr dt. So we are going to replace the r with 4, dr dt with 3/2. We get 12 pi units of the area over the units of time, 12 pi square feet per second precisely. This is an exact answer. If they ask for an approximation, just follow how many decimals. Otherwise, you don't have to write that. This is the exact answer, and this is what we must write. What does it mean? The area of the balloon is increasing. Why is it increasing? Because this is positive. At what rate? At the rate of 12 pi square feet per second. Okay. So it's pretty straightforward. There's a typo there, okay? Okay. A 20-foot ladder leans against a building. The base of the ladder slips away at a rate of 2 feet per minute. Find the rate of change of the height of the ladder when the base is 12 feet from the building. This is an application problem. The setting is not given. You have to come up with the setting. It is a must. So here's the building or the wall. Here's the ladder leaning against it. Okay. So we are going to define our variables, the sides X and Y. The ladder has a length of 20 feet, which is fixed. So we say C equals 20 feet. As the base of the ladder slips away, going this way, it creates a speed of dx dt, because we called it x. Dx dt equals 2 feet per minute. We want to find the speed by which it comes down, right? The height of the ladder, the dy dt, at a precise moment when the base x is 12 feet. So we're going to write dx dt is 2 feet per minute. dy dt is missing. X is 12 feet. That is, again, the drawing and the translation. I can't emphasize this enough. And so having said that, what do we notice here? Pythagorean theorem says a squared plus b squared must be c squared, and a and b are the legs, in this case x squared plus y squared. C is the hypotenuse. It happened to be fixed at 20, so we get x squared plus y squared equals 20 squared. This is the one we're going to differentiate with respect to t. So this is 2x dx dt plus 2y dy dt. This is 400. A number results in 0 when you differentiate, regardless of the independent variable. Now notice we have everything except at x equals 12, when x is precisely 12, we don't know what y is, so we have to plug it into this one to find the value of y. This is 144, this is 400. We are going to move the 144 and subtract it from 400, 256. Square it, square root it, and y becomes 16 feet. Now we have everything. Let's plug in. So 2 times 12 times 2 plus 2 times 16 dy dt. And we end up with this one is 48. This one is 32. You want dy dt, you want to move the 48 and make it negative. Divide both sides by 32, and it results in dy dt being negative 3/2 feet per minute. So obviously x is increasing, therefore dx dt is positive. Y is decreasing, it must be negative. So the height of the ladder is decreasing. At what rate? At the rate of 3/2 feet per minute. When we mention decreasing, it means negative. You don't write decreasing and then negative 3/2. Now, before I move on to the next question, please understand, as this thing moves, so as it moves away, it creates dy dt, and this angle, as well as this angle, they change also. So we can make up questions about those. So continuation of that type of question: a 20-foot ladder leans against a building. The base of the ladder slips away at the rate of 2 feet per minute. Okay. Find the rate of change of the angle between the ladder and the ground when the base is 12 feet from the building. So identical question, but a different part we are interested in. So it's the same thing here, as you can see. So again, we have to define our variables. We define them again, x and y, and of course, c is fixed at 20 feet, and dx dt is 2 feet per minute. So far, absolutely the same. Over there, we were interested in dy dt. Now we are not interested in dy dt, the angle between the ladder and the ground. So specifically this one, if they said between the ladder and the wall or the building, would be this one. So in this case, d theta dt is of interest to us. And again, we write exactly the same thing we wrote there. dx dt is 2 feet per minute. d theta dt is missing at a precise moment when x is 12 feet. So in related rates, we are going to relate the quantities that we know and the ones that we are looking for. So we do know dx dt, so we want to relate x and theta. First and foremost, understand that if you want to find the sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse. So we should know both of them. In the case of cosine, the adjacent is x. Of course, the hypotenuse is 20. And in the case of sine, the opposite is y, and the hypotenuse is 20. Now, granted, we did find y in the previous page, but you should always go with what's given. Therefore, we must work with this one because x is given. Okay, always try to work with the given. So if I'm Differentiating, I'm going to differentiate this one. I get minus sine theta because cosine, just cosine, the derivative is negative sine theta. But remember, theta is a function of t as well. D theta dt. And now the right side, I'm going to rewrite it so everybody can recognize this as 1 over 20 times x. So it is 1 over 20 times, now x differentiation gives you dx dt. And minus sine theta is minus y over 20, d theta dt is missing, 1 over 20 dx dt. Now, pretty much we have everything. Again, I'm going to remind you of the Pythagorean theorem. X squared plus y squared equals 20 squared. And I'm not going to go over that again. We did that in the previous page, and we found the y to be 16. So over here, minus y over 20. That means minus 16 over 20. D theta dt, 1 over 20. And now I'm going to replace the dx dt with 2. Now, because both sides have identical denominators, 20, just drop them. You don't have to move anything. That means the left side is negative 16 d theta dt, and the right side is positive 2. So if you divide both sides by negative 16, you get d theta dt. So let's divide this by negative 16 and this one by negative 16. And d theta dt becomes negative 1 over 8 radians per minute, units of theta over units of time. Theta is always in radians unless otherwise mentioned. What does it mean? The angle between the ladder and the ground is decreasing. Why is it decreasing? Because it's negative. Decreasing at what rate? Rate of 1 over 8 radians per minute. Falling sand is forming a cone-shaped pile. The volume of the cone is increasing at a rate of 54 pi cubic inches per minute. The height of the cone is twice the radius of the base. Find the rate at which the radius changes when the radius is 6 inches. So what is a cone shaped? We should know it looks like that. The base has a radius r. Here's the height, and the volume is 1/3 pi r squared h. So that's a piece of information from geometry slash trigonometry, algebra, you name it. Geometry mainly, we should know. And so that's one piece we need. Now we're going to go back and reread it again. So the volume is increasing at this rate. That means dV dt is 54 pi cubic inches per minute. Height, h, is twice the radius. H is 2r. Find the rate at which the radius is changes. So find the r dt. At what point? When r equals 6 inches. So this is the translation of this question. Now, bear in mind, of course, we are differentiating with respect to t, but this itself is a function of r and h. And of course, you need to use the chain rule and the product rule and all of the above, but there's no need for that. We are interested in dr dt, so we make everything a function of r by replacing h with 2r. So 1/3 power squared times h is replaced by 2r, we get 2/3 power cubed. By the way, just in case if we're interested in dh dt, we would replace the r with h over 2. That's the way to do it. Now, so dv dt, we're going to differentiate this because dv dt is given. We're going to differentiate this. dv dt, it starts with this number. This is a multiplier coefficient, the number. So dv dt is 2/3 pi. And now all you have to do differentiate r cubed. And r cubed, when we differentiate, we get 3r squared dr dt. It simplifies to 2 pi r squared dr dt. All you have to do, plug in what you have, find the missing one. So the VDT is given, R is given. Let's plug in. 36 times 272. So we have 72 pi dr dt on the right side. We are going to divide both sides by 72 pi. And of course, pi and pi cancel each other. 54 and 72, they're both divisible by 18. It gets 3/4 units of the radius over units of time, units of the top over units of the bottom. 3/4 of an inch per minute, which means the radius of the cone-shaped sand formation is increasing. Why is it increasing? It's positive. At what rate? 3/4 of an inch per minute. Example 5. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between them changing at 4 p.m. from noon to 4? Please recognize the time is 4. So first, the setting. This is an example that cannot be done. It's impossible to do without the setting. So at some point it starts, okay, and it ship A and it's going to the right or east, and the other one is going up or north. So we're going to say, here's what we have. This is the north side, okay. At noon, let A sub 0 be the position of ship A, and let B sub 0 be the position of ship B to begin with, and they have a distance of 150 kilometers between them. And again, this moves this way, this moves that way. So A moves east at 35 kilometers per hour. Let X be distance traveled by A at time t. Similarly, B moves north at 25 kilometers per hour. Let Y equal distance traveled by B at time t. When that happens, it covers X amount. The total is 150. So what is left is 150 minus X. This is X, this is Y, this is 150 minus X. We don't know this distance AB, we call it C. So we are going to say dx dt is 35 kilometers per hour. dy dt is 25 kilometers per hour. A has sailed east X kilometers. The remaining distance to B sub 0 must be 150 minus X. So this is explanation of the situation. So as it goes this way, it creates the speed dx dt, or 35 kilometers per hour. As this moves this way, creates the speed, we're going to call it dy dt, is 25 kilometers per hour. And z moves this way, creates dz dt, which we are looking for. So dz dt is what we are looking for. So having said that, let's just write what we have. And of course, from noon to 4 p.m. is 4 hours. So here's what's happening. dx dt is 35 kilometers per hour. dy dt is 25 kilometers per hour. T equals 4, the difference of 4 p.m. and noon. This is how we arrive at it. What are we looking for? dz dt. And so when we look at Pythagorean theorem here, a squared plus b squared equals c squared. This is 150 minus x quantity squared. This is y squared, and this is z squared. So understanding how we arrive at this equation has got to do with the setup of the setting. So having said that, we are going to differentiate both sides with respect to t. So this one, 2 times the same thing to the power of 1 times the derivative of the inside. This is 0, this is minus dx dt. This one is 2y dy dt. This one must be 2z dz dt. And basically, we are practically done. Of course, x after 4 hours, remember t is 4, and it's doing 35 miles per hour. So x must be 4 times 35, y must be 4 times 25. So x is 4 times 35, which is 140 or 140 kilometers, and y is 4 times 25 or 100. And so putting it into this, we can also find the value of z, and then we plug it into this one. So 150 minus x, that means 150 minus 140. Quantity squared plus y squared, that means 100 squared, and it's equal to z squared. This is obviously 10. When you square it, you get 100. This is 10,000. They add up to 10,100. So z must be the square root of 10,100 precisely. So let's always, the intermediate steps must be precise, everybody. So put the precise answer. So in this case, we are going to replace the x with 140 times minus dx dt is so 35 plus 2 times y, which is 100 dy dt is 25. That's the left side. The right side, now we have a 2 times z, which is this number, square root of 10,100, and dz dt that we are looking for. Notice, first and foremost, this is 2 times some number, this is 2 times number, this is 2 times some number. So first of all, drop the 2's from both sides. In essence, you're dividing both sides by 2. Then this is ten, and therefore 10 times negative 35 is negative 350. This is 100 times 25, so 25 put 2 zeros. So the sum of these two is 2150. So basically, dz dt has this coefficient divided by this number. So dz dt is this one divided by this number. Again, that's an exact. You put it into a calculator and roughly becomes negative 21.4 kilometers per hour. And you're going to write the distance between the ships is increasing. Why increasing? Because it's a positive value. At what rate? 21.4 kilometers per hour. A spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he's 4 meters from the building? Again, I can't do this. This can't be done without the setting. You have to set it. Okay, you have to draw it, and you have to define your variables. So here's the light. Here's the wall. And the distance between the two is 12 meters. And the man walks from the spotlight towards the building, the wall, the building, this way. So it looks like this. Here's the light, here's the wall, and here's the man 2 meters tall. Okay. The man covers X amount. Okay. And this one, we call it y. We have to define our variables. Okay. So as the man moves this way, it covers some distance, for example, x, it creates the speed dx dt. So when the man covers x feet this much, his speed is dx dt, which is 1.6 meters per second. And by the way, if this is x, this is 12, this must be 12 minus x. So this is x. This must be, if the total is 12, this must be 12 minus x. And dx dt is 1.6 meters per second. So remember, here's the guy. As he moves, please understand, for example, if he goes further here, then the y is shrinking, okay? So it's important to understand that. So at this point, his shadow covers y feet with the speed of dy dt. And as I mentioned, this shrinking is coming down. Dy dt is missing and is of interest to us. So this is the setup we need to understand. So we're going to repeat the same thing. Let me first erase my work. So we are going to write dx dt is 1.6 units meters per second. Dy dt is missing when he is 4 meters from the building. This is the distance he has from the building when 12 minus x is 4. So it's important to understand, read this. He is 4 meters from the building, 4 meters from the building. That means the distance from the man to the wall, 12 minus x must be 4. That's the meaning of it. Okay. So if 12 minus x is 4, obviously x is 8. And we are going to use the small one and the large triangle as similar triangles, reminding everyone what we mean by similar figures. Corresponding angles are identical or equal, and corresponding sides are in proportion. Okay, so if you look at the small one, this again, this is the small one. Okay, and then this one is the big one. The two are similar. Why are they similar? These two sides are parallel. Or you can say this angle is in common. These two are 90 degrees, then these two must be identical anyways. So if this is the case, again, I need to erase my work so you can see what's going on. There are different ways of setting them up. Okay. You can say y, for example, from the big one over 12 from the big one, and corresponding to y is 2. Y and 2 are parallel. Do you see that? And x corresponds to this 12. X is from the smaller one, 12 is from the larger one. So we can write y over 12 is 2 over x. And cross product y times x equals 24, and y is 24 over x. And we are going to differentiate. So I'm going to rewrite this as 24x to the power of minus 1. So it becomes clear that when you differentiate, this is 24 times negative 1, x to the power of negative 2. So minus 24 over x squared times dx dt. I'm assuming no one has any problem differentiating this, okay? So dy dt, differentiation of this gives you minus 24 over x squared, and x is the dependent variable, so times dx dt. So all we have to do, plug in the x equals 8, and dx dt equals 1.6. This is one of them goes away. This becomes -3. And 1.6 divided by 8 is 0.2. And -3 is -0.6 meters per second. Units of y over units of t. That's how you find it. What does it mean? The length of his shadow is decreasing. Notice as the man moves away, then as I showed you, the y decreases. So the length of his shadow is decreasing. At what rate? At the rate of 0.6 meters per second. And we do use positive because we are mentioning that it's decreasing, okay? A cylindrical tank with radius of 10 meters is being filled with water at a rate of 7 cubic meters per minute. How fast is the height of the water increasing? Draw a diagram, include units. So obviously it's a cylindrical shape. Here's the radius, which is fixed at 10 meters, okay? And the water is just moving. In this case, we are adding water. And so what we should know is that the volume of a cylindrical shape is pi r squared h. This one is being filled with water at 7 cubic meters per minute. This is dv dt, r equals 10. And how fast is the height is changing? dh dt is missing. So that is understanding the question and putting it into symbolic format. So we have dv dt, so let's differentiate this. dv dt. Now, please understand, pi r squared is fixed because r is not changing. The radius is fixed. So pi r squared times now h differentiated dh dt. There are a couple of different ways to do this. This is one way to do that. At this point, r is replaced with 10, dv dt with 7. This is obviously 100. So 100 pi, divide by it. So dh dt is 7 over 100 pi. Units of h over units of t, meters per minute. Now, and we're done with that, but one other way would be right here, before we move on, we change the r to 10 because it's a fixed number. So pi r squared, by the way, lowercase r or capital V is r is replaced with 10, everybody. So 10 squared is 100. So you can work on that. So when you differentiate, you get 100 pi. dv dt is 100 pi. And now differentiate this as dh dt. And that gives you exactly the same thing. So either way is fine. It is probably faster and easier to write this. And of course, now the height of the water is increasing at the rate of 7 over 100 pi meters per minute. Why is it increasing? Because this number was positive. If the minute hand of a clock has length r in centimeters, find the rate at which it sweeps out area as a function of theta. Well, here's a circular shape of a clock. Here's r, here's theta, the central angle. Okay. And we should know that the area of a sector is 1/2 r squared theta, and S equals r theta. So this is S. This is the area we're talking about, okay? So reading the question again, if the minute hand, so a minute hand of a clock has some length, it's fixed at r centimeters, find the rate at which it sweeps out area as a function of theta. So A equals 1/2 r squared theta. R is fixed, and we want dA dt. It's important to understand R is not changing. Therefore, when I want to differentiate this to get to dA, so dA dt is, well, 1/2 r squared is a fixed number that is not changing. All you have to do times, now theta becomes d theta dt. Then that's it, okay? Now, this is a general case, okay? If a minute hand of a clock has this length, find the rate at which it sweeps out area as a function of theta. That says 1/2 r squared dr theta. For example, in 1 hour, the minute hand covers, as you know, a minute hand covers exactly a complete revolution, 360 degrees, or 2 pi radians per hour. D theta dt happen to be 2 pi radians per hour. So in a complete revolution. So therefore, now we can replace that. So dA dt becomes 1/2 of r squared times 2 pi, and 2 cancels out the 2, and we get pi r squared. Now units of area over units of time, centimeters squared per hour. Again, if they give you the time. Another example, in 1 day, it covers 24 hours. Remember, over the course of 1 hour, a complete revolution. Over the course of 2 hours, 2 times a complete revolution. Over the course of 24 hours, 24 times a complete revolution, 360 degrees, or 2 pi radians. So 24 times 2 pi radians per hour gives us 48 pi radians per day. So all we have to do, d theta dt must be replaced with that in 1 day. So 1/2 of r squared times 48 pi. 48 divided by 2 is 24. So 24 pi r squared, units of area over units of time, centimeters squared per day. A street light is mounted at the top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he's 40 feet from the pole? So again, the setting is extremely important. So we are going to draw a setting as follows. So this is 15 feet tall pole. This is a 6 feet tall man, and it's getting away, okay, walking away from the pole, and has the speed dx dt 5 feet per second. So let's understand that. Here's the tip of the man's shadow. Okay, so as it hits the head, okay, tip of the man's shadow. So when the man covers this much, x feet, this is x feet. That's why we call it dx dt. So when he covers this much, the tip of the shadow covers this much. His shadow covers y feet. So he covers x amount. The tip of the shadow covers from where he started all the way to here. Therefore, given dx dt is 5 feet per second, dy dt is missing when x is 40 feet. X is the distance from the pole. a 15-foot tall pole. Okay, so this distance. So this one is the following. I hope you see that this distance is 15, this distance is 6, this is x, this is y. And if this is x, this is y, what is this one? Y minus x. Okay. Small and large triangles are similar. This little one and the big one, they are similar. And as I mentioned, if this is x, this must be y minus x. And so there are several different ways of writing this concept of a similar figures. For example, this one, these two sides, okay, this from the small one, this from the big one, 6/15. You always use the numbers that you can. And then y minus x from the small one, y from the large one. And we write 6/15 is y minus x over y. And that's it. Practically, you're done because this is the most important thing. Setting up, coming up with this equation, cross product, 15 times y minus x, 6 times y. So we distribute the 15, we get 15y minus 15x. We move this one becomes positive. We move this one and subtract it from 6, 15y, we get 9y equals 15x. And because we want to solve for y, we're going to divide by 9 and reduce the fraction to 5/3. So y equals 5/3 x. Now we want to differentiate. We get to dy dt equals 5/3 times dx dt. So 5/3 times dx dt is 5. So it becomes 25/3 feet per second. And we're going to say the tip of his shadow is moving at the rate of 25/3 feet per second. It's positive. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius of the balloon is 20 centimeters, how fast is the radius changing? Similar to what we have just seen. Again, spherical shape, the volume for it is power cube. We should know that. So what is given? dv dt. The point of this question is dv dt is negative, so minus 8 cubic centimeters per minute. And at the moment that the radius is 20 centimeters, how fast is the radius changing? We want the dt when r is 20. So this is the symbolic explanation or translation of what is given. And this is a formula from geometry we should know, or algebra. And so again, we're going to repeat what we did in the very first question. So we are going to differentiate this dv dt is 4/3 pi. And now we're going to differentiate r cubed, which is 3r squared dr dt, as we did that before. Is to cancel each other. We get 4 pi r squared dr dt. We are going to replace the dv dt with -8 or with 20. As you know, 20 squared is 400 times 4 is 1600 times pi is 1600 pi. We're going to divide both sides by 1600 pi. So this becomes negative, this becomes 200. So we have -1/200 pi. Units of r over units of time. That means centimeters per minute. Roughly, with a bunch of decimals, -0.001592 centimeters per minute. We say the radius is decreasing. Why is it decreasing? This is negative. At what rate? At a precise rate of 1/200 pi centimeters per minute. Notice we don't mention negative because we said decreasing.